Thank you very much. Yeah, so my talk will be on combinatorics, and the relation with physics is that original miracle was discovered by physicist O.Ogievetsky, who worked in Marseille. And the question, it was some kind of representation theory at the end of the day. And he was asking the following, calculating the following question. Consider Young diagram and start to feel, consider this poset, consider it as a partially ordered set. And maybe with n elements, and consider all various functions to non-negative integers which are monotonic. And you want to make this functions, all functions of this poset to integers, monotonic. And you do some geometric series. You take element in your poset and values of this function. And this one can write it's some certain polynomial divided by 1 minus t plus t square minus t to power n. And he was interested in this polynomial. And eventually to reduce to some calculation, to some matrices. And it originally started with Young diagrams. And it have a series in one variable, but turns out there is something very remarkable here, goes very, very general. And so it was discovered a year and a half ago. I learned from this from a problem of his colleague, of not O.Ogievetsky, but S.Shlosman, who was my colleague from Institute for Problems of Information Transmission, who came here at IHES to celebration of 100th anniversary of Ising model. Yeah, and told me this story. And then kind of for about 1 month was a lot of excitement. And then everything was solved by, we have a lot of courses, but really one person prove everything is, it is W.Sawin. And somehow, because there are so many authors, it's still not, we didn't really agree on what is the final text, so it's not, this text doesn't exist, yeah. So what is it? It's now this kind of the general situation is you have any finite partially ordered set with n elements. And I start this really stupid example. Now we have just three elements, and only 2 of them are comparable, like you see here. Yeah, 2 comparable. And now I consider a larger finite set of all possible linear extension of this partial ordered set, or total orderings, extending this partial order. Or one can say you consider monotonic maps from your set to standard interval, which are bijections. So you enumerate preserving the order. And here you got 3 enumerations, yeah, because this largest guy should be 3 or 2. And now what I do, I can first construct some metrics filled by permutations. In n letters, the entries, each pair of orderings will be ratio, because you get 2 maps to 2 bijection with 1 by n. So consider the quotient to get automorphism of 1 by n. Yeah. So in this case, I just started. What I drew before, it's kind of like indices of the matrix, all these 3 enumerations. Now I can forget about my partial order, just it's various enumeration of my set. And now I just go from to another. For example, if I consider first column, it's 1, 2, 3. And now I read these things 1, 2, 3. So a permutation will be 1, 2, 3. Now I read 2, 1, 3, following this order, get 2, 1, 3, and here it's 1, 3, 2, and yeah, so this ratio. So I have 3 by 3 matrix filled by permutations. Now each permutation has it just kind of like function from 1 to n to itself, and it's kind of goes up and down. And I just forget about the whole structure of permutation. I just keep track whether its function goes up. 1 to 3, from first to 2 I go up, and 2 to 3 go up. But 2, 1, 3 I go down and up. Yeah, so I replace my matrices by permutations by these diagrams of up and downs. And more conveniently, I just say that I have sequences of zeros and ones. Up will be 0, down will be 1. And I put its indices of some variables. So I get matrix of filled by some variables. A priori, I get 2 to power n minus 1 variables. Huge number of variables. So I get this square matrix, and you can calculate it in this case, even by hand, I think. Yeah. So, and you see that eigenvalues are this integer linear combination of variables. And in fact, the first eigenvalue is the most important one, you see, because this matrix is stochastic. Actually, I'll go to maybe next slide. Maybe I show this kind of random next example. I take now partial ordered set with 5 elements. There are 10 different variables which appear in the matrix. I just to save notation, I denote like from A1 to A10. They repeated some here, so it gets this huge matrix, and then one can calculate eigenvalues to get again this nice list. And can go on and on.
Indices are multiplicities.
Indices are multiplicities. Yeah, you see the eigenvalues seems to be repeating here. Okay, now what is our general theorem? That for any finite poset, you construct matrix like in this manner. So eigenvalues are integer linear combinations of these variables. Yeah, so what is going on? This matrix is just by definition linear combination of matrices which whose entries are zeros and one. You can see where each variable appears, you get kind of pattern of zeros or ones. And so you get this matrices labeled by the sequences epsilon. And first thing which is kind of very surprising, how it's possible that you get kind of linear pencil of matrices that eigenvalues are linear combination of things, because matrices in general do not commute with each other. Yeah, matrices don't commute with each other, but what's going on? And yeah, that's the main miracle. And this matrix is stochastic. So the sum of each row is the same, or 1, 1, 1, 1, 1 is eigenvector, and it has some certain eigenvalue. And eigenvalue will be certain sum with positive coefficients. I think this is the last one in this example, for example. And this polynomial, terms of this expression correspond to monomials of this polynomial. Yeah, so it was original discovery. He wanted Ogievetsky wanted to calculate this polynomial and found a way that there is a stochastic matrix. So there are many ways to calculate. None of them is canonical, and this gives you this polynomial. And then he just by fun he tried to calculate eigenvalues and discovered this remarkable property. So it had no reasons all as eigenvalues.
Sorry, but eigenvalues of a stochastic matrix are inside unit disk. There are those bounds of Kaplan.
Yes, yeah. No, if things are positive, yeah, okay, yeah. But it's kind of formal variables now.
Okay.
Yeah. Yeah. What is explanation? What's going on that we can calculate eigenvalues of linear combination of matrices in linear ways? That the reason that the matrices can be simultaneously put in upper triangular form. And then what you really do, you calculation of diagonal terms. Or more precisely, you get a filtration on algebra of functions or space on which this thing acts. And the filtration is pretty long. It goes up to n/2 and choose 2. Yeah, so there's certain filtration on the algebra of functions on the set of total ordering, which is preserved by all operators for each individual sign epsilon, is such that induced operators on associated graded spaces are commute with each other. So we can further choose some common basis and make it strictly upper triangular matrices. So this filtration, I will describe you actually what we have final answer. What is this filtration? First I kind of discovered by computer, but then when I had the proof, everything became clear. So the low space, because it's upper triangle, we know it's kind of, we have this eigenvector 1, 1, 1, 1, 1. So it's function 1 on my set, and it's one-dimensional common subspace for these all operators. Yeah, and so it explains stochasticity of the matrix. What is the next space? I consider a linear subspace of functions spanned by this constant one, and all functions labeled by two pairs of my partially ordered set. Any two elements, A and B, in partially ordered set, distinct elements, gives a function on space of total orderings. Namely, the functions with values plus and minus 1. The value of order A could be larger or total ordering to be or smaller as total ordering to be. That is the case. But we consider the real valued function or integer valued function. So I get these functions, and I call this function linear. Then I can multiply the function, call this products quadratic, then cubic, and so on. So I just generate strictly multiplicative filtration, and eventually it exhausts all my space. And the claim in associated gradient, you get commuting operators. Now the proof. Yeah, so that's a kind of remarkable structure. You get filtration by powers of some subspace, which call linear functions. And operators commute. There is eventually came to some kind of like very huge universal class of such families of matrices. Namely, I do the following. I fix some capital N greater than 1 and consider some n-dimensional cube. N-dimensional cube has 2 to the power n vertices. And then the cube has a lot of faces, actually 3 to the power n faces. Like interval has this side, the interval itself and right-hand side, and the same for high-dimensional cube. And for each face, you have a natural map from the space of vertices to itself. Just imagine, I don't know, kind of like two-dimensional cube, and we want to contract everything to a vertex. It's clear what is the map. Each vertex goes to itself, and these things go, just map all set of vertices just to one guy. Or you can make projection to, I don't know, to the low part. So this will go to itself, this go to itself. Yeah, I get plenty of such retractions of a set of vertices. And each face defines a retraction. And retract the whole cube to one face. So it have a maps from a space of faces to the space of set of faces to space of maps. And in fact, composition of two maps will be again given by some face. So the space of faces is certain monoid, non-commutative monoid acting on this set of vertices. And it has huge number of elements, 3 to the power n, acting on 2 to the power n elements. Now, so I get maps from set to itself. It's induced by pullback maps on the space of functions. And here's the key lemma that these operators corresponding to this maps preserve this filtration, certain filtration. The filtration is exactly restriction of polynomials of degree 0, 1, 2, and 3 to the space of two vertices of a cube, because cube sits in a Euclidean space, so we can restrict it. And on corresponding associated gradient spaces, these operators will commute. And proof is very, very simple. One just can go to, because it's tensor product, one can go to case of one, like interval. Yeah, it's very simple case. So we get 3 operators acting on function on the set of vertices, which is 2-element set. And these operators are these matrices. It's kind of like correspond to the whole interval with identity map. You contract to one vertex or another vertex, and we will get it will be transposed to how it acts actual vertex because it's in space of functions. And you get 3 operators acting on 2-dimensional spaces. It preserves 1-dimensional space of constant function. It's 2-dimensional space, so you get flag. And definitely they commute in a quotient because quotient is one-dimensional, so there's really no mystery here in this case. And then you take tensor product and get the whole story in arbitrary main dimension. Now, what will be this number capital N? It will be n choose 2. where n is number of elements in some abstract set without partial order. Now I just consider some abstract set. So I got some general stories, then I descend eventually to our framework. What will be vertices? Yeah, 2 to power n choose 2, you can interpret as a set of tournaments. So imagine that, like, I don't know, you have something like 4 players, tennis players, and they each meet another and somebody wins. It's kind of like for each of them you choose ad hoc who wins against whom. Now, so there is a set of tournaments. It's obviously vertices of this huge cube, because you have independent choices for each edge. Now, in this case, I want to say something. There are some special phases in this huge cube, which correspond to filtrations. And filtration on a finite set, it's a surjective map to some ordered interval, which I can really try to think it's kind of like strictly increasing family of subsets which exhaust the whole set, and all steps are non-trivial. So it's a filtration, or you can see that this guy maps to 1. You encode it to maps. The lowest level goes to 1, the next goes to 2, and the next goes to 3. It's just the same information. Yeah, and this filtration gives a face on this cube of tournaments. Namely, what is going on? Suppose you get some tournament, you got put arrows somewhere between these things. In a way, I want to make a new tournament. And in new tournament, I keep arrows in each level, but force arrows from larger level to small levels go down. Yes. So some arrows I keep, and the rest I force to be something. Yeah. So I get filtration. So I get a very special class of faces, and also there are very special class of tournaments in this situation. Namely, tournaments when we have total order. So we can see who's won the gold medal, bronze, and silver, and so on. Yeah. So we can say it's without any doubt. Yeah, so there are total orderings. There are only n factorials of them, and there are because all number of tournaments it's huge, and here's this little just n factorial between this 2 to n square over 2 special tournaments, and there are special faces, and number of faces also much smaller than number of all faces. It's some Stirling number. Yeah, so the first fact is if you restrict to these special faces and special tournaments, and then retraction corresponding to this filtration preserves the class of total orderings. So we can make it, instead of this huge 3 to the power of a huge number of matrices of size 2 to huge power by itself, we get some smaller matrices with the same property. And so, because it's kind of like part of this matrices from the big problem, we still get integer and Givelli properties. It just will be minors of huge matrices, and not all matrices are used. And how this procedure goes? Yeah, suppose you get a tournament which comes from a total order. So on the whole set will be some total order. But now you get kind of smallest piece. You keep the order it is here. Then on next piece you also get this some total order and so on. And then you, or maybe I should go, things go. And then you just connect one by another by setting one group is larger than another, and that will be gain a total order. So it's clear why this is preserved a set of total orders. Now finally I go to our things when I get partial order on my set. It's not just abstract set, it also has some order. Then we get among filtrations, we get those which are compatible with this order. And this filtration will be monotonic, not just surjections, but surjection preserving order. And also total ordering, also it will be bijection, also preserving order, so it's exactly linear extensions. So you get again smaller part of the same game. And one can check immediately that if this story that you get some certain monoid acting on some set, and it's work out here. So we consider all filtrations and ordering per compatible with partial order, we still get closed picture. So you get plenty of operators with integral eigenvalue property and also some filtration by powers of some restriction of polynomials of bounded degrees. Yeah, so go this. No. Yeah, now what we do. So we get many operators labeled by these filtrations. Now we are organizing some groups, namely choose an ordered partition of my number, any ordered partition by non-trivial pieces. And then take sum over all operators corresponding to all monotonic maps, surjections, such that sizes of level sets are given by this partition. Again, you get many operators with the same property, integer eigenvalue property. But now we get 2 to the power n minus 1 operators, because number of such ordered partitions 2 to the power n minus 1. And I started with the problem. I said get another 2 to the power n minus 1 operators corresponding this m epsilon, corresponding to sequence of 0 ones. Of course, this indices which you put for t, like ordered partition, or epsilons which you use for my operator m, are the same when called as a subset from 1 to n minus 1. An obvious way. Yeah, so we can replace the indices by subsets. And then, kind of again, little thinking gives you that. Oh, sorry, this is misprint. It's Tj sum of mg prime. Yeah. And then you can use inclusion-exclusion formula, can write its inverse sum, and we are done. Yeah, okay. Yeah, so that's essentially the proof. Yeah, it's eventually very elementary. When we discovered it, there are many authors. We discovered it, and we communicated with some people, with Richard Stanley, and then eventually it turns out that in some ways this thing was kind of known. There was some result by B.D. Gara, Handon, Rockmore, in combinatorial description of the spectrum of the Zetlin library and its generalization hyperplane arrangement. It was in 1999. There was some paper which known in some community, from which kind of really impossible to see directly, but people, yeah, so it's kind of, we are divided. So the result is not really new, but in a certain sense, yeah, but it's very well hidden, yeah. So there's a special case which I tried before the proof appeared. Just let's try to make a really very stupid thing. Consider trivial order. No two elements are comparable. Then any ordering is the total ordering for this trivial order, getting factorial orderings, and the automorphism group of the set acts on this and commute with the whole story. So you see that my operators commute with the action of symmetric group, and what we get to get regular representation of the symmetric group, and some operator commuting with regular representation. So it acts on some isotopic classes, because regular representation gets some of copies of irreducible representations, and yet here get some eigenvalues on each for each class of irreducible representation for each partition. So a priori I expected to get for each partition to get some numbers, and then get many not numbers, it's linear combinations, get many linear combinations. But surprisingly, this it gets very strange. There is a lot of coincidence, and you get number of represent all different eigenvalues, linear combinations, only partition number. Exactly how many pieces, yeah. But doesn't mean that each piece gives only one eigenvalue. They appear here and there, but they kind of distributed some bizarre way. So get decomposition of a regular representation symmetric group and some of highly reducible representations labeled by partitions. And then I kind of calculate dimensions of these representations. It turns out the dimensions are equal to the cardinality of conjugacy classes. You see, if you have a group n factorial, one can write sum of a dimension of some corresponding representation squared, yeah? It's a usual formula, but also it's sum of a lambda number of elements of conjugacy classes. So you decompose the same number in the sum of in different summands, and here we get different summands. And then one can make immediately the obvious guess: what is this representation corresponding to conjugacy class, which has dimension equal to the size of conjugacy class? It should be induced representation for some character for stabilizer, because conjugacy class is quotient by centralizer, and centralizer of any element of cyclic group which corresponds to representation is, one can say it's like cycle of length 1 multiplicity 1 and cycle of length 2 multiplicity 2 and so on. So the centralizer is a product of lengths of cycles on each product, we can Riesz product, symmetric group acting on a product of cyclic groups. Yeah, it's kind of, again, obvious if you have kind of a lot of, let's say, cycles of length 3. What commute with them, you can rotate them independently or permute them, yeah. And each vector maps to its corresponding cyclic group, namely you forget about symmetric group, and you get kind of sum of cyclic groups. You take sum, which is of coordinates in symmetric group, which will be invariant on symmetric action, get some homomorphism of those things to cyclic group, and take kind of the most naive irreducible character, and take some of it, and claim these guys are induced representations. It's again, I make the guess, and the guy who proved everything, W.Sawin, proved it as well. Okay, yeah, and yeah, so that's essentially the end of the story.
Questions? Yes?
Tiny naive question. When you have one of those posets with many arrows, like the W shape that you have, many eigenvalues have multiplicity 1. Then the eigenvectors, do they also have nice components?
No, because eigenvectors, no, there are eigenvectors on quotient space, but they really depends on some kind of very nasty way in the whole space, because variables do not actually commute.
Okay.
Yeah, so the formals are not nice. Yeah.
So in a special case when you have hyperoctahedral group, you have when k equal 2.
Yeah.
This is some special your business.
Nothing.
Oh, and you like arbitrary.
Yeah.
You were mentioning some monoid at one point.
Several points. Yeah. No, I told you that this faces of a high-dimensional cube form a monoid, because we can control, and then one can specify to the situations like flex form a monoid and so on, and then we get some interesting non-commutative rings with some nilpotence property. And yeah.
I missed the connection between the original problem that you explained and this question of, I'm sorry.
No, you get certain polynomial here. They wanted to calculate.
Can you about this polynomial?
This polynomial, it's sum of monomials with some positive coefficients, and this monomials essentially correspond to leading eigenvalue for the stochastic matrix. It will be some you can read from any row for this matrix. Yeah, but the beauty is that you don't have specific row to choose. You get kind of like different forms for the same things, but not one canonical one. Yeah.
Other questions, remarks, or
Do you know, are there any other finite groups where the regular representation has a decomposition that looks like that?
I have no idea, yeah.
So we thank the speaker again. Thank you.